Hi, so we're looking at the second part of 2.5. This is looking at abiotic factors and how we might be able to measure biotic factors and how we might be able to measure biotic factors in an ecosystem study, particularly if we're interested in different populations of organisms living within an ecosystem. These are really relevant for an IA if you're interested in going out and examining ecosystems within the area. So we're looking at some different systems that we can use in order to capture different organisms. So the first one that we're looking at is this pitfall trap. So it's exactly what it sounds like. So it's a little pit. So we dig out an area. Okay, this one is lined and it's also covered. Okay, the cover is really to prevent it from collecting with rain. So the idea is organisms might wander in and then they'll become trapped in this little pit. We cover it so that it doesn't flood, because if it floods, then our organisms might drown before we can go get them out. So if you chose to do something like this, you just want to be careful that you're checking it fairly frequently, because we do not want the organisms to die in the traps. Okay? Next we have sweep nets. So this would be a common way to capture things like insects. So sweep nets come in a bunch of different sizes, and the netting actually comes, or the mesh, so this part, okay, this part comes in different sizes as well, depending on if you're trying to capture really tiny things or much larger things. So when it says description, you're just writing information about it. So you could find these in a bunch of different sizes. Again, really helpful with insects. So when I was in college, one of my assignments was to make a large insect collection, and I had a net so I can go out and try and capture some flying organisms. So a lot of times you might see them wandering through a field and sweeping these over the plants in order to capture as many things as they can. Then this one, both of these sound kind of silly, but there's tree beating, which is exactly what it sounds like. So it'd be like you got a big stick, you hit a tree, and you pretty much see what comes out of the tree. The idea is you could create you could have a piece of cloth at the bottom to capture the things. So as they fall down, you'd collect them, and then you'd examine them and see what had been in the tree. And then there's also a contraption called a pooter. So a pooter is kind of like a little homemade vacuum. So it's a sealed container, and there's two tubes coming out of the container. So there's this long tube here, and then there's another tube. Okay, this tube is, it looks a little shorter, but also it's blocked off with a piece of gauze, and that one's going to come up. So it would be, for you, you'd be walking around holding this container. You'd have this tube, and that's where you'd put your mouth on it, and you'd suck up the air. And the idea is to suck up or kind of vacuum up any small little organisms, so maybe spiders or insects, into this container. So if you see them on the ground, you can go over and just suck them up into the pooter. So the gauze is clear, so the gauze is there so that the animal gets kind of sucked into and trapped in the container without making its way into your mouth. All right? So it's a very interesting contraption. This is just an image of someone who's doing the tree beating. So he's got this net, essentially, or a piece of fabric to capture whatever's falling out of the tree. And of course, you can imagine if you're hitting a tree with a stick, you're going to get some leaves and some twigs in there as well. Now let's move on from terrestrial systems into aquatic systems. So this is looking at kick sampling. So this is really common in streams. So kick sampling is, again, very much so what it sounds like. So you're walking along the stream, kicking at the bottom, kicking at the bottom of the stream, and then you want to make sure that the water that you're kicking up and the materials that you're kicking up are flowing into a net. So you could have one or two people working on this. So then you might free some small organisms, possibly your little invertebrates, maybe things like crayfish even, and you would capture them in your net and be able to examine them. This is actually pretty fun if you've never done it. It's a pretty fun thing to do if you've got some waterproof boots, or in the summer, if you don't need them, you might not need them depending on the water quality. You can go and take a look at this. It's super interesting. And you can capture different invertebrates and decide like if those invertebrates are indicators of good water quality or poor water quality. So it's super interesting. So here's another image. This time we have two people participating. So one person kicking and walking, and the other guy's holding, a net to capture things. So when we're looking at biotic components, this is why we have our dichotomous keys. So just a reminder, our dichotomous keys, we want them to contain physical characteristics so that people could observe the organisms and then classify them while they're out in the field. Okay, and I think the people who turned theirs in so far have done a really great job. So you're doing exactly what you're supposed to be doing. But the ideas of doing the dichotomous key first was just that if we go out in the field, we have to be able to identify the organisms and distinguish them. Okay, most importantly, maybe we don't know the species names, but we're able to distinguish one organism from another based on its physical characteristics. So just practicing the powers of observation. Then we have two calculations that we need to be aware of. One is the Lincoln Index. So the Lincoln Index is a way of calculating the population of mobile organisms for one species, so just for one species of organism. So this is, again, an estimate, so it's not going to be 100% perfect, but this is our calculation. So to figure out the approximate population, we have to go and capture some of the organisms within a species, mark them with something, whether it's an ear tag, fin tag, a little band, so they put bands around the feet of birds, or you could try something a little bit fancier depending on what you're looking for. And then you have to release them back into the population and then come back at a later date and try to recapture them. So here we're going to get three different important numbers. So every time you do this, you have to count the number that you caught in the first sample. So the first time you went out and caught some of the organisms, N1 is the number of organisms you caught. Then you release them right after they're tagged, and you see what happens. So N2 is the number of organisms you caught in the second round. So let's say I did this on one Saturday. I caught some birds in an area, I tagged them, and I released them. And then I came back the following Saturday and tried to capture another group of birds in that area. So N2 would be the number of birds I caught on the second Saturday, and N sub M is the number of marked organisms that I caught in the second time, so in the second sample. So let's say I went back on the second Saturday, okay, and I did find some of my marked birds in the group that I caught. So NM is the number of marked birds that I found. So of course, all of these calculations have some limitations. So this is looking at some of the assumptions of the Lincoln Index. So of course, some of these assumptions are a little bit less realistic than others. So one is we assume complete mixing. So that means if we release the organisms, they're not going to be, shunned by their peers. They'll be able to, go back into the community and behave normally. The other one is that the marks can't disappear, so it has to be something fairly permanent. The marks don't hurt the organisms, okay, nor are they advantageous, so it can't be something that would make that organism like the coolest organism in the entire area. And that we're equally able to catch them every time. So this is a really hard one to think about, because it's hard to know, like, if we caught an organism, if it would be less likely to be caught a second time in a similar trap. Then this one too, I think, is a little bit silly, but it says there's no immigration, emigration, births, or deaths within the population. So one way we could try to limit that is by doing them the trials in quick succession, so that there's not going to be a lot of change within the population in the area. And then that trapping organism does not affect their chances of being trapped a second time. Okay, so if they wander in once, they're just as likely to wander in another time. So this is a very silly example. So we're saying that we're looking at these animals, that we're going to mark them. okay, after we capture a group of them. The way we're going to mark them is with this flag. So we are catching a population, we're marking them with this flag, and then we're releasing them back into the environment. The idea again is that all the marked ones will go about their regular business, doing whatever they did before, okay, and be able to mix with the other organisms. So now we see, some time later, they're just kind of mixed in with the whole population. So they're not all together, okay, they weren't shunned by everybody else. They're just mixed in with everybody. Then we capture a new sample. So let's say this time we grab this group of organisms, and we can see that some of them are flagged, so we had marked them, and most of them are not. So now we're trying to figure out an estimate for the population size, so we have to do the calculations. So let's go back and look at our numbers. So this was the first group that we captured. So there's 1, 2, 3, 4, 5, 6, 7, 8 individuals. This is the second group that we captured. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 individuals. And then we're looking at the number that were marked in the second sample. So we had 1, 2, 3, so only 3 with the flags. And now it's just some basic math. So we do 8 times 9, and then we divide by 3, which is going to give us 24. So our estimate of the total population in this area is 24 of these organisms. Okay, I'm actually going to pause here for a second, so if you want to try this, give this a shot. So it's the same type of calculations. This is actually an excellent question. Would possibly make a really good quiz question or something similar. So if you're looking, this is Lincoln Index information that was taken on a population of gorillas, and then it's asking you, deduce or try to determine when illegal hunters were most active in the forest. So looking at the change in population over time, when do you think illegal hunting was at its peak? Because there has been a lot of illegal hunting of the gorillas for meat, okay? And then it asks to explain the long recovery time for the population. So then we actually have to think outside of the box of just this lesson and think back to the past couple topics, all right? So this is an excellent question. Hopefully we will have some time to talk about this in class, because I do think this is a superb question and would be an excellent quiz question. So now we're going to look at diversity. So diversity is about multiple species, not just one species. So the diversity is about the quantity, the number of different species, and how many organisms there are of each species. So just so you know, when we're doing the calculation, the larger the number value, the greater the diversity. When we're looking at diversity, we can describe it in a couple different ways. So richness and evenness. So richness is just to do with the number of different organisms or species in a particular zone. So maybe we find that there's 25 different bird species in a certain zone. Okay, that would be fairly rich. Evenness has to do with how balanced the populations are. So if we have 25 different bird species in a zone, okay, if almost all of the birds, if 90% of the birds are the same type of bird, then that's not as diverse as if they have very even populations. So if they had, about 4% of the population belong to each of those species. That would be more diverse because it's more even. So that distribution is key. So these are the numbers we get. So taking a look, we have D equals N times N minus 1. Okay. So the capital N is the total number of organisms in the ecosystem. And then the lowercase n is the number of individuals of each species. So at the bottom we have the sum. Okay, so we're dividing the total number of organisms in the ecosystem multiplied by total number of organisms in the ecosystem minus 1. So all of this divided by the sum of the number of individuals of each species times that lowercase n minus 1. Now, very similar variables, right? So we just want to make sure we understand how to run this calculation. So remember, high values for D means